Okay, we're gonna start lesson 4.3, which is about horizontal and vertical asymptotes. This lesson is gonna look a lot like an advanced functions lesson with basic concepts. And what I'll try and do is introduce the calculus concepts as we need going on. So today we're talking about definition of a rational function. A rational function basically is when you have a function that is made up of two components that make it look like basically a fraction. So what we have to know is that f of x and g of x are polynomials, which I'm not going to get into. The domain of a rational function consists of all real numbers except zeros of the polynomial in the denominator, which has g of x is 0, right? So the denominator can equal 0. Usually that's when we get our asymptotes. The zeros of h of x, the whole entire function itself, are really the zeros of f of x, right? That's kind of easy to remember. Basically, the zeros are basically, we forget about the denominator in the rational function. We just solve for the x-intercepts of the numerator. Vertical and horizontal asymptotes, it says the graph of a rational function has at least one asymptote, which it may be vertical, horizontal, or oblique. We should have covered all of these concepts last year in advanced functions, but I'll try and go through some ways of actually figuring out this way as well. This lesson. When we're doing obliques, will be a little bit different. Vertical asymptotes can be found where the function is undefined. And basically, what we do is we look at the denominator and see where it's undefined. And we do this by setting the denominator equal to 0 and solving. And that will be giving us our vertical asymptotes. Since the vertical asymptote is opposite to the domain, right, the solutions will be values that are not allowed in the domain. A little bit of a typo there, but I think that's understood. The graph of a rational function never crosses a vertical asymptote, but it may cross a horizontal asymptote. I'm going to add something else in here. I'm going to add that in rare cases, um, the function may cross an oblique asymptote. Okay, it's very rare that it happens, but it actually can, and I think it's above and beyond the scope of what we're trying to do in this course. General rules on finding a horizontal asymptote. Um, Again, this is review from last year advanced functions, so I'm not going to really go into it. Basically, you can review for yourself. If you have any questions, you can always email me, message me. We can do a video chat, whatever the case is. But these are the rules, right? Where we have to see that the n and the m are right there. Okay, so basically, we're looking at the coefficients. For an oblique asymptote, for rational functions, linear oblique asymptotes occur when the degree of the numerator is exactly one more than the degree of the denominator. So that's pretty easy to kind of remember. So what we did last year in advanced functions is we did either long or synthetic division to find out what the answer would be, and that answer, disregarding the remainder, would be our oblique asymptote. Let's do some examples. So in the first example, it's asked us to find the vertical and horizontal asymptotes. So we don't have to do all the fancy derivatives and everything else, right? So let's see what should we do first. For the vertical asymptote, right? So for the vertical asymptote, what we have to do is we have to set the denominator to 0 and try and solve, right? So if we try and solve for this here, what we're going to get is 2x squared is equal to negative 3. X squared is equal to negative 3 over 2. X is equal to plus or minus the root of negative 3 over 2, which really gives us imaginary numbers. So really that means there's no vertical asymptote. For the horizontal asymptote, basically what we have to look at the degree of the numerator, degree of the denominator, and see if there's a difference. So for the degree of the numerator, right, our degree of the numerator is going to be 4, our degree of the denominator is going to be 2, because they have the same value where m is equal to n. That means we can just use this technique here. So we actually have a horizontal asymptote of 2. And I'm going to put that in before I forget. See if it matches our graph. And we can see that in this case here, this is our horizontal asymptote where y is equal to 2. We can see that the function actually crosses the horizontal asymptote. So the last thing we have to do is we have to find our what else do we have to do? That's all we have to do really. We just have to find the horizontal and vertical asymptotes. So we're done. Another way of finding the horizontal asymptotes is by a new technique. Well, it's not a new technique. I showed my class last year. I'm just gonna move this over a little bit. Move it over a little bit. That over a little bit. I showed my class last year, right? You can't see it. And it goes something like this. So change the color so we can actually see a new concept. What I'm going to do is I'm going to take the limit of the function. I'm going to take the limit of the function. And what I'm going to do is I'm going to factor out the a term if you want, right? So in this case here, my a term would be my 4x squared. And what I'm left with is 1 plus 5 over, it's really 5x over 4x squared. So I'm going to just put 4x because the x on the numerator cancels out, minus 1 over 4x squared. And on my denominator, what I'm going to do is the exact same thing, factor out my a, so I'm factoring out my 2x squared, and what I'm left with is 1 plus 3 over 3x squared. Well, I didn't specify what we're taking the limit of. What we're going to do is we're going to take the limit of this function, right, as x approaches positive infinity. And this is pretty cool. So if let's pay attention kind of here, right? In the outside of the brackets for the rational function, the x squares can cancel out the x squares. So I have my 4 and I have my 2. That's what's left over. Inside the bracket in the numerator, if I were to make x a really big number, a million or something like that, what we'd see if we put this into our calculator, that's going to approach 0. And same concept, if I put x a million into our calculator, I'd put this into our calculator, we get that goes approaching 0. And the last thing, that too is going to be approaching 0. Sorry, I forgot a bracket over here. So what is left? Well, we have the 1 and we have the 1. So 4 times 1 is basically 4, and 2 times 1 in denominator is also 2. So really what we have in this case here is we have the limit, if we clean this all up, right, of 4 over 2, which is basically simply 2, which matches up with what we have over here. So new way of doing things. You should have seen this in advanced functions. Let's try the next example. I know for a fact that this graph is not correct, so we'll see if our calculators support what I'm saying. So we're going to do the exact same thing. Again, for my vertical asymptote, what I'm going to do is I'm going to make x minus 1 equal to 0, or I can say x is equal to 1. So we're going to have a vertical asymptote at x equals 1. So let's make sure the scale is right in this graph. X equals 1. I'll just drive it down there right now. So this is x equals 1, our vertical asymptote. For our horizontal asymptote, we have to be careful because we have the plus 6 at the very end. So we kind of have to see if there makes a difference. Maybe it will, maybe it won't. For the horizontal asymptote, I'm going to say that there's none. And we'll prove this in a few seconds. Since our n is greater than our m, that means, therefore, there's going to be an oblique asymptote. There will be an oblique asymptote. Funny spelling. All right, so now we got to figure what it is. So let's try this out. Before I do anything, I have to worry about what's happening with that 6. So really what we have is we have our x squared minus our 3x, that stays the same. I'm going to extend this all to be x minus 1, but we also have to take account that 6. So to make that work out, we'll have to look something like that. I'm going to expand and simplify. So we're going to have x squared minus 3x plus 6x minus 6 all over x minus 1. We really don't need the brackets. I don't want to confuse people. And simplify one more time. And we have x squared plus 3x minus 6 all over x minus 1. So now that we did this, we can still see that our vertical asymptote is the same, but for our numerator, it's done something slightly different. That 6 actually makes a big difference, and I think this will be kind of interesting. So let's do this. I'm going to take the limit as x approaches infinity, and we're going to do the same thing we did in the question above. In the numerator, and factor out the first term. So we're left with a 1 plus 3 over x minus 6 over x squared. And on the denominator, we're going to factor out the x, and we're left with 1 minus 1 over x. And we're going to treat this the same way we did the last example. We're going to plug in a value for x that's really big. 1 million, 10 million, whatever the case is. And when we do that, what we're going to notice is that's going to approach 0, that's going to approach 0, and that's going to approach 0. So what's left? Oh, we can also cancel out an x with the x up here. So all that's remaining is really x. So when we simplify all this, we get x as our oblique asymptote. Now, here's why I said that this doesn't match up. Our oblique asymptote will look something like this. So clearly we know that, we know that the function can cross an oblique asymptote, but like I said, I know this function is incorrect. If we do this here, we know it cannot cross a vertical, so it's not crossing the vertical. So this part of the function is actually correct. That's supposed to be a sharp turn. All right, and for the other one, the actual curve looks correct as well, but because we have an intercept of 6, and it's going to go down to the 4, and then it just ties down somehow like that. So that's what the green function actually is, what the pre-printed function should look like. And we can see with our asymptotes that actually makes sense. Still, it's a function, it passed the vertical line test. It's not crossing the asymptotes, so we're good. We got one more. Let's try this out. Every type of question that we do has a little different trick. I'm going to factor this one here, and just to save some space, I'm going to put it right to the side. Looking for a product sum of 10 and 7, respectively. So we're going to have x plus 2, x plus 5, that should work. And we can see that those cancel out. The x plus 2 in the numerator and the denominator cancel out. So what we have then is we have a function which is going to be just basically 1 over x plus 5, right? So because we canceled out a value, that is going to produce something called a hole. So we know, well, let's go through it in stages. Let's do our vertical asymptote. Our vertical asymptote is when the denominator is set to 0 So in this case here, we want to see what happens when we have x plus 2 and x plus 5, which is equal to 0. That's going to produce x equals negative 2 and x equals negative 5, right? But we know that this one here is a hole, and we'll find the point. So basically, all I really have to draw is my vertical asymptote. I'll draw that right now. So this is my vertical asymptote of x equals negative 5. The other one's going to be a hole, which we'll determine in a few seconds. The next thing we're going to calculate is the horizontal asymptote. Basically, I have to look at the function. My n, in this case here, is 1 over my m, which is 2. So n is less than m. Therefore, my horizontal asymptote is going to be y is equal to 0. Okay, which again, if I transfer that over, that makes sense. That's horizontal asymptote, y is equal to 0. All right, to find the horizontal asymptote using the new method that I've demonstrated above, I'll do it here in green. Let's do this. So what we're going to do is we're going to find the limit as x approaches infinity. And what we're going to do is we're going to factor out the a term. So we're going to factor out the x. And what we're left with is 1 plus 2 over x. And for the denominator, we're going to factor out the first term. So it's going to be x squared. And what we're going to have left over is 1 plus 7 over x plus 10 over x squared. When we clean this up, when I say by clean this up, when we plug in a value for x that's really, really large, what's going to happen is we're going to have that go to 0, that go to 0, that go to 0. And then we have one of these x's canceling out, right? So really what's going to happen is, if you think about it, when I plug in a really large value for x now, the numerator is going to be 1, and the denominator is going to be a really big number, undefined, which really means it's approaching 0. So what I can do is I can just say that my horizontal asymptote is 0, which supports what we did before. Now, the last thing that we did not do is we did not find the value of the hole. So if we want to find the value of the hole, we know that the hole is going to exist at x equals negative 2. So for the hole, I'll do it up here, right? We're going to put an f, sorry, not f, it's h in this case, h of negative 2. Now, because we canceled negative 2, it's redundant to put it back. So what I'm going to do is I'm going to put negative 2 plus 5, where we have h of negative 2 is equal to 1/3. So the hole, I'll do it in red, is going to be at, where did I say it was? Negative 2 and 1/3, right there. This is our hole at negative 2 and 1/3. Kind of hard to see, but it's there. The last page, the key ideas, is basically a summary of everything we've done so far. I think it's pretty self-explanatory. You can look it over and see for yourself. And again, the only really big new concept for some of you may be taking the limit as x approaches infinity of the function to find out what the horizontal asymptote is. But we technically can still do it using the comparison of the degree of the numerator versus the degree of the denominator and the coefficients. And that's all for now.